This is the not my fault executable we've been using so far. We have seen that in multiple different occasions. So we have seen this particular crash high IRQL fault. Been using this so far. Whenever we needed to crash something, we were using this particular bug check. There are other issues which we're going to see: buffer overflow, code override, so on and so forth. Then there is this hang tab. In that we have 3 types of different hangs, and then finally a leak. So in the leak, we have leak paged and leak non-paged. We have 2 kinds of paged pool and non-paged pool leaks. First, we're going to see the 32-bit version of this particular binary and driver in a 32-bit operating system. Then we will switch to 64-bit, and all these issues which we are seeing right here, we will see in 64-bit as well. Post that, most probably we will be only looking at 64-bit in the real world. In Windows Server, in production, 99% of the cases, it's going to be 64-bit. And we will be focusing on 64-bit. After the exercise of Not My Fault, you will be convinced how similar 64-bit and 32-bit. It's exactly the same. That is one thing we need to achieve from this Not My Fault exercise. We have this crash right here, high IRQL. So we are going with the high IRQL. I'm going to crash. All the debugger, everything is attached to the 32-bit VM. So as I was mentioning, it's 32-bit. So it's broken into the debugger. We have seen this before multiple times. Just for the completion, we are going to look into it. I have typed bang-alias-v. That is a command being executed. So I clicked on the button. Bang-alias-v is in progress. So as you can see here, it is giving IRQL not less or equal. This is nothing but access violation. So we are trying to access a memory which is not really valid. That's what we're gonna see. The bang-alias-v is finished. This is the memory address which is being a reference, BEF74030. That is the address which the crash is happening. And as you can see here, the IRQL is 2, which means that a lot of interrupts are masked. It is at dispatch level, which means the paging, it cannot page out or page in a particular page. So which means that if we touch a paged out page, we will crash because the IRQL is at DPC level. Because of that reason, any memory which is not valid, any page which is not valid, if you access any of those pages, we will get this particular error or this particular bug check code. What are the conditions for this particular bug check to come up? Driver IRQL not less or equal. You should be at a higher IRQL and paging should be turned off. And then we are accessing a page which is not there in the memory at this point in time. Then we will get this particular bug check code. What we're going to do is we're going to do a bang pte command on this particular address, the memory reference address. The command which I'm typing is bang pte, then the address. So in the result, we can see that the page has been freed. It's not a valid page. That's why we are getting a page fault exception and we are having problem translating the address. Now, if you are doing a DC on that address, we are not getting anything because that address is not valid at all. So there is no backing page associated with it. So it's an empty address. So in user mode, if you are trying to access this address in a normal scenario, we will get an access violation. This is similar to access violation. The IRQL is 2. Now, if you want, we can do a dot trap. I'm going to do a dot trap here. So I'm going to just click here. The trap will take us to the exact same context of the crash happened. The address is pointing to move EAX dword PTR ESI. There are 2 addresses being accessed. One is EAX and dword PTR ESI. What is inside ESI? In the ESI, we have that address, which is BEF7430. This is the address we are trying to dereference. We are trying to read from. And that address, as you can see here, doesn't have any value in it. And no surprise, we are crashing. One more thing I would like to highlight here is the nature of this bang pte command. Bang pte command, what it does is it converts the virtual page to physical. This is the virtual address which we are trying to convert to physical address. It will go through the page table entries and find out a couple of things. One is the flags. Let's draw the page table. This is the page table. We've been doing this so far a lot. One is the virtual address. Now there is physical address. And then there are some flags. The virtual address in this case is BE F74030. That is the address we are trying to convert. There is no valid physical page available. There is no corresponding physical page because it's an invalid page. We will see a couple of examples of bankpd command in which we will see a valid page. Then we will see how it looks. Normally, this is how it looks. This is the page table directory entry. This is how here also it should look. There will be a PFN, which is the corresponding entry to the frame number in the RAM. And these are the flags. So different flags. We will see what are these flags as well quite soon with the help of the debugger documentation. We have some exercises coming up in the Not My Fault itself. There are different types of flags and then the physical address. Right now, bankpd command just convert virtual address to physical address, just like the CPU does. This is the command to convert virtual address to physical address. So that is all I wanted to talk about the first issue, the high IRQL fault.